Yeah, so welcome everyone to the last lecture. I thought since we had a 2-week break and also because it's the last lecture of the course, I'm going to review what we have learned so far to put this in a bigger picture. So the past 4 lectures that we had can be summarized by a discussion of the infrared effects in asymptotic flat space, the discussion of how soft factorization theorems in quantum field theory imply a certain asymptotic symmetry called BMS symmetry, how we can map 4-dimensional quantum field theory scattering statements or how can we rephrase them in terms of 2-dimensional statements on the sphere that lives at the conformal boundary of asymptotic flat space, and the discussion of what soft symmetries or soft theorems imply in this new basis for quantum field theory scattering. And we're going to continue with this discussion today, but we will also add to it the discussion of how collinear singularities of amplitude imply the operator product expansion in celestial CFT. And if there's time, we'll talk also a bit about dressing and infrared divergences. So let me start with a little more detailed discussion of what we have learned. So in the first lecture, we drew these Penrose diagrams of asymptotically flat space. We discussed causal structure of the space-time, and in particular how we introduced the notion of asymptotically flat space, which starts with Minkowski space, but then has subleading corrections, and these subleading corrections can be characterized by these 3 quantities here: the boundary mass aspect, the angular momentum aspect, and the gravitational data that's related to gravitational radiation. And we've discussed how the first one is an angular density for the mass or the energy, the second one for angular momentum, and the time derivative of this boundary mass aspect gives the flux of energy across null infinity. Then once we have set up, once we have decided what our fall-off conditions are on the metric or other fields that we might consider in the spacetime, then we can ask what are all the residual symmetries that obey this structure. And this led us to the notion of what's called asymptotic symmetry group, which is the group of all the allowed diffeomorphisms modeled out by the trivial ones. So the trivial ones were the ones that are non-trivial in the space-time, but then at the boundary, the gauge parameters fall off too fast to have any effect on the physical states. While the allowed ones include transformation of the physical states, so as a change in the physical states, and so as an actual symmetry. Then we discussed a particular class of asymptotic symmetries that follow from the boundary conditions that we picked, namely an infinite enhancement of supertranslations, which are called infinite enhancement of translations to supertranslations, where the 4 global time and space translations get infinitely enhanced. And also an enhancement of rotations to so-called superrotations, where the 6 Lorentz generators are infinitely enhanced. And in the literature, there's a distinction between whether we allow superrotations that come from a symmetry parameter, or rather a vector field that's singular but meromorphic, or non-meromorphic, and distinction is then called extended or generalized BMS. Then we discussed how to make the scattering problem well-defined if we start from some states in the past and go to some states in the future and have some non-trivial scattering in between. We found that we have to impose matching conditions of the fields as we approach the future of past null infinity or the past of future null infinity, so the region near I0. And so, for example, we found that we should impose that a certain condition for all these asymptotic data, but also for the symmetry parameters. And here I've just written down the one for the boundary mass aspect. So it's identified as we go, as we approach I0 from both null infinities. Then we looked at what the action of these newly found asymptotic symmetries are. So super translations act on one of our metric component ZZZ by this shift, by this change of CZZ itself, but then also has this inhomogeneous term, which we found or which we focused on later on. And then superrotations similarly have some terms that which act on the data, but then also this inhomogeneous piece. And then we wrote down a chart for these supertranslations and superrotations, which involves the boundary mass aspect with the supertranslation parameter f, and the angular momentum aspect with the superrotation vector field y. And much of this discussion, so here, this was in the first lecture, is stuff that has been discussed in the 60s. And then in discussing this in the context of scattering and a matching condition, we went into the 2010s. So we've covered quite a number of decades here in arriving at the point where we want to say, is this asymptotic symmetry now a symmetry of the scattering? And so in order to see that, we looked at the commutator between the charge and the S matrix, or rather we wedged this between in and out states. And we found that indeed this gives 0. And so we found that BMS is a symmetry of the S matrix. And in order to show this, what we did was we split the BMS charge at the future and the past boundaries, or plus minus, into a soft part and a hard part. And in particular, found that the soft part here contains the insertion of a soft graviton, which then lets us use the soft graviton theorem. And the hard charge acting on the state gives a certain transformation of these metric components. And massaging these expressions then led us to the result that indeed the commutator of the charge with the S matrix vanishes. Okay, then in the third lecture, so this was the first two lectures, in the third lecture, we massaged the expressions that we got from the soft theorems a little more and found that actually one can recast them as word identities. For the leading soft graviton theorem, we found the word identity that is one for a smoothie current. And for the subleading soft graviton, we found one that's a word identity for a stress tensor. Now, for the leading soft graviton, or in other words, the supertranslation symmetry, we found that this word identity in particular contains a factor that 1 over z minus zj, where zj is where the j labels the jth hard particle, and the energy of the jth particle. And for the stress tensor word identity, we found these expressions, or rather we found one where there was also a connection and a spin connection, but I flattened everything here, so this is just the word identity for the two, for a stress tensor. And in particular, we had this operator in here, the omega d omega operator, and we wanted this to be diagonalized. So that means that we have to change the basis. So when we want to go to a basis that diagonalizes the action of omega d omega to just give a number. So including the 4D spin or the helicity, this number would then be called H. And we found that this new basis, the boost basis, can be obtained by a certain map that takes us from the momentum basis to a new conformal basis. For massless particles, we found that this is achieved by doing a Mellin transform in the energy. And that was kind of natural because massless particles already hit the conformal boundary at null infinity. So there's already a natural point on the sphere at null infinity that the particle enters or exits the space-time. And so we wanted to trade the energy for some parameter that will be related to this H. That parameter is delta. And then, so this was for massless particles, and then for massive particles, because they don't naturally hit a point at null infinity, we had to, what we did was we looked at a hyperbolic slicing of Minkowski space, and then we integrated over this, the coordinates for these hyperbolic slices, and this integral included also a scalar back-to-boundary propagator. And so that gives us a way to map wave functions in a momentum basis to wave functions in a new basis, in a conformal basis, where now these wave functions not only transform as spin S fields in 4 dimensions, according to Lorentz transformations, but they also transform as 2-dimensional conformal primaries. So we're after some intrinsic description on the celestial sphere at null infinity, which we call celestial CFT. And in such a theory, we would like to have objects transform exactly in that way. And then starting from these conformal primary wave functions, which we constructed for any spin essentially, we can then obtain, so, and these wave functions still depend on the bulk point as well as a boundary point. By taking an inner product of these wave functions, integrating them over Cauchy slices, so integrating over X, we then obtain two-dimensional operators, which are labeled by the conformal dimension delta and the 2D spin J, and a boundary point W and W bar. Then, in the fourth lecture, we used this knowledge and this map to actually define the asymmetric matrix in this new conformal basis. So we recast scattering processes in the momentum basis via this map as correlation functions on the celestial sphere, where we can interpret this as operator insertions in certain regions on the celestial sphere that are assigned to or related to particles entering at scry minus and exiting at scry plus. So this is for massless. And we call this object a celestial amplitude. So this is just the usual amplitude, but now written in a different basis. And why can we do this? We can do this because the SL1.3 Lorentz group is isomorphic to the SL2Z global conformal group. And we can embed the 4D boost and rotation generators, or we can relate the 4D boost and rotation generators to the global conformal generators, L0, L plus minus 1, and the same for the barred ones. Okay, so far so good. Now I'm going to say a bit more in detail about Lorentz generators and translation generators. This is elementary, by which I don't necessarily mean trivial or obvious, but it's rather important. And so I will give a few more details here. But maybe let me ask first if there are any questions about any of the things that we have discussed for the last 4 lectures. Everything clear or everything unclear? Hopefully clear. OK. So now let me say a bit more here. We already discussed this in the last lecture, but it's perhaps worth repeating. So here we look at the generators for n equals minus 1, 0, and 1. And these satisfy the centerless 0, 0, or rather the SL2Z subgroup. And the same for the barred ones. And in particular, we discussed the action of the Lorentz generators on these 2D operators here, which I will now label instead of delta and J with H and H bar. Delta was H plus H bar, and J H minus H bar. And we found that for an operator at the point W and W bar, this can be expressed as follows. So we have the appearance of H, and then we have also derivative with respect to the 2D coordinate W. And in particular, we have these operators that have these plus minus labels according to whether they are associated to regions for scry plus and scry minus. OK, so delta here, the H plus H bar is the boost weight, and J, which is H minus H bar, is the 2D spin, which is identified with the 4-dimensional helicity, potentially up to a sign. And now let me maybe, so this is the action of on these operators, but as a simple example for how this acts on wave functions, let's consider, so these wave functions satisfy box phi equals 0 for the massless case, and then accordingly for the massive one. And let's consider just the scalar case, which is just given by the spacetime vector dotted into this null vector Q, where this null vector Q was given by 1 plus WW bar, W plus W bar, I, W bar minus W, and 1 minus WW bar. And now actually let's look at the case where we are at the point WW bar equals 0. So this is 1, 0, 0, 1, where this then reduces to 1 over x0 minus x3. And I forgot to write the power delta here. And now let's check that the action of L0 gives us the conformal dimension, and well, the action of L0 plus L0 bar, and that the action of L0 minus L0 bar gives us 0 because this is a scalar, as well as the highest weight conditions if they are satisfied. So, okay, so this is the wave function, and now the embedding of this conformal global, or the relation between these global conformal generators and the Lorentz generators that I have chosen in this. Well, it's rigid but not completely fixed. So L0 plus L0 bar is related to the boost K3, and this is given by x0 dx3 plus x3 dx0, while the difference is given by J3, and that's I times x1 dx2 minus x2 dx1. And now with that, you can check that L0 plus L0 bar on phi delta gives delta phi delta, and L0 minus L0 bar, sorry, I called this a different phi, is 0. And then you can also check that L1 phi delta and L bar 1 phi delta is 0. And then you can rotate the generators in order to see that this is satisfied for generic locations, W and W bar. Okay. So, yes?
So can you remind us what are the hermiticity conditions for K3 and J3 on the...
Yeah. Let me first continue this discussion here, and then I'll talk about the conformal multiplets, and we can talk again about the hermiticity.
Yeah, so just to finish with the microphone. So, because I thought, for example, in CFTs, sometimes they have hermiticity conditions that relate K3 to J3, but maybe that's related to radial quantization or something. So the question is, in the quantization that you're using.
Yeah. So.
But you can answer later if you want.
We discussed last time naturally follows from the unitarity of bulk Lorentz transformations, was that L dagger n is minus L bar n, and then the same for the barred ones. While in the one that you're used to, is L dagger n equals L minus n. And well, we can come back to this when discussing null states. But so this is the one that naturally follows from when you use the, let's say, the Klein-Gordon norm. And so this follows naturally from the 4D bulk. But if you use a different inner product, then you can arrive at this hermiticity condition. So
I guess the answer, sorry, this basically implies that K3 dagger is K3 and J3 dagger is J3, right?
There's a bar.
No, I mean in terms of the Lorentz generators, K3 and J3, they're just Hermitian. And assuming that they're Hermitian, then you get the hermiticity. Should I think about it like this?
You can.
Is it correct, what I just said?
Well, if you did that correctly, then yes. But my point is that, so this is currently what hermiticity condition you arrive at, what inner product you use, is currently an active area of research. And we, naturally what you get from the bulk is this, what you expect from the boundary is this, and various nice things follow from this. And it's not, so this has a bulk motivation, while this doesn't yet. So it would be very interesting to see. So this relation involves having in the definition of the inner product, having the shadow transform in the definition of the inner product, which is not something that from the bulk is currently well motivated. So it would be very nice to get a bulk motivation for why we should be using a different inner product, and with that different inner product, we would be landing on that. And then everything follows more like in usual CFD, and shadow transform also has the nice feature, or maybe light transform if we go to from 3,1 to 2,2 signature. It has the nice feature that other things that look strange from our sort of bias point of view of what we know about vanilla CFDs makes other things also look nicer. So it's currently, it's not dictated what you should do. This is what is motivated from the bulk. And this you get if you do something else, but a bulk motivation for why you should get this is currently outstanding. So there's not really much more that I can or want to say here, because this is still under investigation.
So just to understand, if you were to do this different inner product, would you just be changing the relationship between L0, L0 bar, and K3 and G3? Is this what it would change? Or it would change the hermeticity, the bulk hermeticity condition on K3 and J3?
I would have to think about it. Yeah,
okay, thanks.
I'd be happy to discuss. Yeah. Okay. So then, good. So let me continue then first with Lorentz translation, Lorentz transformation we already did with translations. So here we already discussed that the momentum generator can be, in the new basis, can be recast as a weight shifting operator. In terms of the h's, let me write them now, d by dh and d by dh bar over 2. And this essentially was motivated by the fact that when the translation operator and the momentum basis acts, it gives us a factor of the momentum, which includes the energy. But then when we Mellin transform in the energy, because we have an additional factor, namely 1 of the energy, what this does in the Mellin transform, so if you add this extra omega, this just shifts the conformal dimension delta. And in terms of h and h bar, this means it shifts h and h bar each by a half. Okay, so this sort of motivates or explains this form. And then what we can do is we can take combinations of the different components of this momentum generator, which are also very useful. So for example, we can take P0 plus P3 or P0 minus P3. And we will call this P minus a half for the plus sign, and plus a half for the minus sign. And then we can also take combinations that involve P1 plus minus IP2. And we will call them plus a half, minus a half, minus a half, plus a half. Okay, and in particular, on this one, the one where we have the plus sign, the minus a half, minus a half. So what we do here, look again at this null vector Q, which was this expression here. So the first and the second component with the appropriate minus, yeah. So the first and the second component just gives us a 1. So this is really just the this weight shifting operator. Okay, and in particular the action of this operator. So now let me write it as, so this acts differently on in and out states. So let me do an eta, which is a plus or minus for in or out, and then let me call the remaining operator once I have sort of pulled out the plus or minus sign. Let me call it omega hat. Because in the momentum basis, what it does, what this omega hat does, if there's an operator that depends on momentum P, it gives the energy. And then in the new conformal basis, the action of this operator omega hat on an operator that has dimension delta is just that the delta gets shifted by 1, or the h and h bar get each shifted by a half. Okay. Good. And then now we can use these translation generators to write down the algebra that they satisfy. So here, so let me maybe, let's do this again. So I have these generators M, or let me call them K and L. And here, K and L run from a plus or minus a half for the global translations. And the algebra that they satisfy, well, translations commute themselves. And then I can also look at the commutators of the Lorentz generators with them. And we have seen some version of this algebra, at least schematically, in one of the previous lectures. So the same for the barred ones. And then I can look at the action of PKL on an operator O, H and H bar at the point W, W bar. And this acts differently on in and out state. So there's a plus minus here. And then we have some powers of W and W bar. Where we see this shift by a half and a half. Okay?
Sorry, Andrea, I think I must have missed this. Did you define this PKL for arbitrary KNL?
No, so here I'm just writing the ones for the global, and I also just restricted to them here. Mm-hmm. But, okay.
Oh, okay, so you're only working with the plus or minus.
So here I've defined the global ones, but you can then also define them for, so these ones for arbitrary, for n in z, and for k and l in z plus a half. And that takes the Poincaré algebra, which I've written down here, so the Lorentz one and the, including the translations, into BMS, the BMS algebra.
And the general definition of these PKLs for arbitrary KNL in Z plus a half is what?
Yeah, you can write it down. So this one just has a 1 here. The one where you have plus a half has an extra Z bar. And these ones have a Z or a Z bar. And then for the general ones, you will have different powers.
I see. So you're just adding powers of Z and Z bar in front of this exponential, and that's it. Okay, thanks.
And actually, let me do that now when grouping these generators PKL into another object. Let me call it curly P, which is given by, or let me call this differently, Mn in Z, n minus a half, m minus a half, and then Z to the minus n minus 1. Oh, sorry, W. By the way, I will probably be writing W's and Z's interchangeably because sometimes I cannot decide which ones to use. So here I'm talking about 2D coordinates. So you can group all the PKLs into this object here. And this object, you can check that this is a dimension 3 scalar. Or it has H and H bar given by 3 half, 3 half. And yeah. And now we're going to see where such an operator with that dimension lies in the conformal multiplet. And maybe before moving on, let me make another comment here. So here we discussed, so this then gives, by extending the range of n and k and l to z and z plus a half, we get the BMS algebra. And then we can also add to it the SUSY generators, if we're interested in supersymmetric theories. So which satisfy following commutator. So this is p minus 1/2 minus 1/2. And with the ln's, they commute. And then we can sort of discuss the extension of BMS4 into super BMS4 and discuss supersymmetric theories. Okay. So then let's review what we learned last time about the structure of conformal multiplets, by which I mean with respect to the global conformal symmetry. So what we found was that if the conformal dimensions of a primary have, of a primary take a certain form, then these primaries have descendants that are also primary. So in particular, we found, and I'm writing here h and h bar, that if you start with a primary whose dimensions are given by 1 minus k over 2, 1 minus k bar over 2, where k and k bar are in the positive entire numbers, then we can generate descendants with it. So in general, we can get the descendants by the action of L bar minus 1 and L minus 1 to some power. But then we found that when this primary has these conformal dimensions, these weights, and we act with L bar minus 1 to the k bar, or L minus 1 to the k, then we get descendants which are also primaries. Or if we start with primaries whose dimensions are given by 1 minus k over 2 and 1 plus k bar over 2, or 1 plus k over 2 and 1 minus k bar over 2, then they have a descendant that is a primary. And so here, minus 1 to the k bar, and minus 1 to the k. And then this guy down here has weights 1 plus k over 2 and 1 plus k bar over 2. Okay, and the action of these L minus 1s and L bar minus 1s, we can see from here what they do. So if you look at operators that are at W bar equals 0, then they just give you essentially they are derivative operators in the 2D coordinates. So acting with L minus 1 to the k is the same as acting with dW k times. And this one, dW bar k bar times. Okay? And then we found, so you don't have to have this full structure. We can just discuss what happens when this primary has primary descendants, or starting with primaries that have these weights when they have primary descendants. And then there's also the degenerate case. And it's worth discussing these different cases because they sort of unify the structure of the symmetries that we get in the conformal basis by looking at what is the analog of energetically soft factorization. Oh, and one other thing that maybe I want to add here is that we can also show that these primaries or primary descendants on the left and right are actually related via the 2D shadow transform, which takes weights h, 1 minus h, and h bar, 1 minus h bar. So you can clearly see that this is the case here. Okay. Now,
sorry, Andrea, would you also have a shadow transform between the upper guy and the lower guy?
Yes, and you would also have, you can also go back up here, and that's related to half a shadow transform. Okay, so now let me discuss we can classify all the conformal primary descendants and put them in 3 different categories, depending on whether the primary that you start with is a radiative primary, by which I mean that the magnitude of the 2D spin is equal to the 4D spin. Or you can start with or you can look at what is the structure of primary descendants when the descendant is a radiative primary, or at the case where both are radiative primaries. And so the first one is, I'm just drawing this diagram again, but only these pieces here. We call this situation type 1, where the descendants here, so the descendants will have 2D spin J prime, and the parent here has 2D spin J, and the magnitude of the spin of the descendant is bigger than the spin of the parent. And the situation is such that these primary descendants are radiative, so the magnitude of their spin is equal to the 4D spin. And there are infinitely many of such primary descendants, and in particular, if you start with, let me just say this. And then we can look at the situation where we start with radiative primaries, and then discuss what they descend to. So now the parent is a radiative primary. And then we have a descendant here, and and there are finitely many of such situations. So here the parents have a radiative, but the primary descendant is not, and we call this type 2. And then there's a situation that is degenerate, which I can sort of write in the middle, which we call type 3, but it's a limit in the sense of these two, which is when the parent is a radiative primary and the descendant is 2. So this is just schematically. And maybe I should have emphasized delta goes down and the spin is horizontal in these diagrams. And this situation here, where the parent is a primary, is the one where we'll find the asymptotic symmetries. Or let's see, the celestial symmetries that have a clear asymptotic symmetry interpretation. This situation here is one where we have, let me call it the most subleading soft symmetries. And it will become clear in a bit what I mean. And these do not have a as clear-cut asymptotic symmetry interpretation as these ones. And then here we have a situation here, we have infinitely many such states. And in particular, we can consider operators that come from wave functions, whose power delta is actually, where delta is sufficiently negative so that this is a polynomial. And then hitting this polynomial with enough derivatives will always give us zeros, and zeros are trivial primaries. So there's infinitely many of this type. And there you will actually get bona fide and null states in every sense because you get zero wave functions. Okay. So this was a little bit schematic, but I think there will be a journal club where Emilio will discuss more of these sort of diamond structures. And so for now, let me then move on to discuss or review what we said last time about the asymptotic symmetries from the point of view of celestial CFD, which fall into this category of conformal multiplets. Yes?
So I have 2 questions. So one is you wrote n there, the minus q dot x to the nth power. So you mean positive powers?
Yeah.
Yeah. And another one in this diamond. If
this was just an example. So
right. And in the diamond there, you said the left and right are shadow transforms of each other.
Yes.
what happens if you do a shadow transform of the top one?
Yeah, that was Monica's question. So from the weights here, you see that that would change from the top to bottom.
Yes.
Yeah.
So top and bottoms are also shadow transforms of each other.
Yeah.
Okay, thank you.
So, okay, the thing is, if you go from left to right, you can show with full generality that this is related. Typically, when you go from top to bottom, because you do a lot of derivatives, you might think that you lose information anyway. So this needn't be the case, and one has to be careful about kernels that where you when you descend, where you get terms that get annihilated, naively speaking, by the action of the derivatives. Yeah. Yeah.
I didn't understand that. Is it worth elaborating? I mean, if I didn't understand your hesitations or your distinction just now. So if the shadow transform is defined as something whose output is doing that operation on H and H bar, then what is the issue?
So I remember checking that the top and the left-right corners are related by light transforms, and then you have, if you put certain number of light transforms together, then you can get to the bottom of this this diamond. My hesitation is just that I don't remember if there were any subtleties that I'm now forgetting. I don't know. Yeah. Okay. So now let me, and by the way, I should have said maybe, so this was, we started in the 1960s, and now we arrive in the 2010s. Sorry, the 2010s. Yeah, we arrive in the, so this goes even up until this year. So what I'm discussing here is basically what has been developed in the last year or two. So it's very fresh. There's a lot of interesting questions that one can ask, many of which will not have been addressed, so those I will not be able to answer. But this is all a work in progress, and there's many interesting aspects that one can think about. So what I'm discussing now maybe started in 2019, and I already reviewed some of it last time. So in the first lecture, we started the discussion of soft factorization properties of amplitudes, which I will denote by A. And we said that when you take the energy of an external massless particle to 0, then you get a factorization of this endpoint amplitude with the extra particle whose energy is taken to 0 in terms of the amplitude without that particle, and then you get these additional factors here. For the leading, so the 1 over omega pole, the subleading, so constant in omega, and then further subleading terms. And we said that we can map the different orders of omega once we do the Mellin transform to different values of the conformal dimension. So here, okay. The Mellin transform these soft theorems, we'll find that there are poles at every value of delta that is associated with the values of the powers of omega here. And in particular, when this number is -1 and 0, as the ones that I have written here, we get the leading, subleading, and then further subleading terms in the energetically soft expansion. And this maps in a conformal basis to celestial amplitudes having poles at these values of delta. And in particular, the conformally soft poles will be when delta is integer for integer spin particles, or half integer for half integer spin particles. Okay. And then we talked about, from the celestial perspective, where the celestial amplitude is a correlation function of operators, we talked about what operators are responsible for this factorization. And relating back to discussion of what identities that follow from asymptotic symmetries, we discussed that the operators that give rise to that, so there are currents, and these currents give rise to these word identities that we have written down before. And so one point to make here is that, so we're looking for these operators at the special values of delta and try to interpret them in terms of asymptotic symmetries. And what we discussed last time is that when these conformal primary wave functions, phi delta j, become pure gauge, then the operators that they define through the inner product generate asymptotic symmetries. And these are of this type 2 here. So the operators would be sitting here, and then they descend, they have a primary descendant, and this primary descendant is important in the discussion of soft symmetries. But that's not the end of the story, because in this conformal basis, for example, for spin 2, we found that there are 2 pure gauge modes, namely the one for where delta, so what this implies is that delta equals 1 and 0 are special cases. And we found that there are only for these values you find pure gauge wave functions, which give rise to these symmetry generators. But then we know that there are more. So for example, there's a sub-subleading soft graviton theorem here, which does not have a clear asymptotic symmetry interpretation. And then there's more terms in the expansions as well. So not being pure gauge does not mean that there is not something interesting here. It's just that the asymptotic symmetry interpretation is not quite clear. So there exist soft or conformally soft theorems or symmetries for which phi delta j is not pure gauge in this basis. And these, so this sub-subleading soft symmetry would correspond to this degenerate type 3 example. And then there are further symmetries which do not have a clear asymptotic symmetry interpretation, which would fall into this category here. Okay, so just to review the ones that we discussed last time. So for delta equals 1, we found this metric mode. So delta equals 1, j can be plus or minus 1. Let me just focus on plus or minus 2. Let me just focus on that. And we showed that this can be written as a pure diffeomorphism. And in particular, if we look at the 1 over r term of the z component, so we look at the graviton state, so the asymptotic state of this graviton, then we find that this is actually given by minus 2 dz squared times some function f. And if you remember what I put in a box on one of the boards that I erased, this is precisely, so this form is precisely the one that you get when you look at the inhomogeneous shift that supertranslation have on some metric component, ZZZ. And then, moreover, you can show that actually the diffeomorphism that this metric, conformal primary metric gives rise to can be written, so the leading component at null infinity would just be given by this function f du, and this is precisely the form of the supertranslation diffeomorphism vector field. Okay, and then we can write down the operators, so O, where delta is 1 and j is plus 2, which is defined via the inner product that we discussed. You can show that this takes the form du dz squared gamma, and then it has this this expression dz squared f nzz plus dz bar squared f and z bar, and this just comes from the general the asymptotic expansion of the general bulk field, the spin 2 bulk field in the inner product. And this is precisely the form of the soft charge for supertranslation symmetry. Okay, now the other pure diffeomorphism here happens when delta equals 0. And here we found that the metric component that has delta equals 0, j equals, I think I chose -2. The ZZ component of that is given by minus u dz cubed yz. And then additionally, we can also look at the shadow transform of this. Here that didn't really matter because the shadow of something that has dimension delta equals 1 will be something that has dimension 2 minus delta, which is also 1. And the two actually agree. But here they do not, those are not exactly the same wave functions. They're just related by the shadow transform. And this has dimension 2, so 2 minus 0. And then we can also write down that mode, and I put a little tilde here to denote that this is actually coming from a shadow of this delta equals 0 mode. And shadow transform flips the spin, so -2 goes to +2. And if I again look at the ZZ component, I find something very similar. And the difference of the spin here will be a difference in these vector fields. So I'll put these labels W and W bar that denote the 2D spin. And I would have to do this here too. Well, let me not do it here, but what I want to do here. So I chose the +2 spin. So I have this particular function f, and here we have particular vector fields y. And similarly, I can write down the diffeomorphism vector field that is given by this, the form of this conformal primary wave function, and I will find that this generates, this is the super rotation vector field. And just as a side remark, in most of the lectures so far, we discussed everything in Bondi gauge, which for this, so for Bondi gauge, but the conformal primary wave functions that we have introduced do not satisfy Bondi gauge, rather they satisfy harmonic gauge. This didn't matter for the leading self-theorem or supertranslations, but for the subleading it matters, and so this vector field that you write down here looks different from the one in Bondi gauge. So we are in harmonic gauge. Bondi gauge is useful for many purposes because a lot of the components in the metric are 0, but harmonic gauge is very useful here too, and in particular it allows us to have this discussion of conformal primary wave functions. Okay, so now let me connect this to these diamonds that I've drawn and to this operator, which was this 3/2, 3/2 operator here. Okay. Yeah, here I wanted to say that also here we can write down the charge. And this will also be an integral. Right here, delta equals, let me write the delta tilde equals to 2, j equals +2. And this is the operator, but it will be also the soft charge for superrotations. So this one is given by, is there a minus sign? Yep, du. D square z square root gamma, and then dz cubed yz ww, and similarly for the one for delta equals to 0. And now let me draw them. So what you can show in general is that, so these are the soft charges for the supertranslation and superrotation symmetry. And what you can show in general that if you have a soft charge for some symmetry parameter xi, which here would be related to this f or this y, then this can be expressed as just a sphere integral of the symmetry parameter dotted into a soft operator. So that will contain the u integrals that I've explicitly written here. And the dot here takes care of any tensor contraction or spinor contraction if we are talking about asymptotic symmetries for supersymmetric theories. And now let me tell you what these soft operators are. So I can draw the conformal multiplet associated to this that contains this radiative primary with of spin 2 with delta equals 1. So that will be at, so that will be of this form. So there are left and right corners, which are radiative primaries. So they have, let me write this here. So they have delta J equals 1 plus 2, and here it's 1 minus 2. And they will descend to some other primary. And what you can see here is that this skips a node. So there is a descendant but no primary. And this is achieved by taking two derivatives or acting with L minus 1 and L bar minus 1 twice. And this lands on an operator which has dimension 3, 0. And this is the soft operator in this expression. So at the left and right corners here, we get the soft charges. That is what we discussed here. So the delta equals 1, J equals 2 mode gives the soft charge. But then we can write the soft charge in terms of the soft operator. So this is the operator that would give you. So here, this is the values of delta that give you the conformally soft factorization theorem. And this is the soft operator that generates the asymptotic symmetry. So yeah, so this guy can be written as the dz squared of this function f with the soft operator 3, 0. And then we can also draw a similar diamond for the subleading soft graviton, where now we start with a primary delta tilde and j, which is 2 and plus 2. And here we start with delta j equals 0 and minus 2. And you can see going down always increases the delta. So going down 3 times from the left or 1 time from the right will change the delta to 3. And j will be plus 1 in this expression. And this is another soft operator. So here we will have a soft operator that can be written as dz squared yz ww for the soft operator 3, plus 1. Okay. So this is super translations. And this is super rotations. And the value of delta and j here, if you translate this into h and h bar, you will find that this is 2, 0, and that those are the weights of a stress tensor. So this charge here is the 2D stress tensor. And then that guy over there is the shadow of this 2D stress tensor. And then for super translations, you can ask, well, we also discussed this Kac-Moody current, the super translation current. So that guy would be a descendant, but not a primary. Would live here. But then we can also look at, discuss the translations in terms of this bottom of the diamond operator, which was this dimension 3 scalar operator that I wrote before, where we grouped the pKLs, into which we grouped the pKLs. Okay, so that concludes the discussion of asymptotic symmetries. There is this sub-leading soft graviton, which I will not talk about, but this essentially has a descendancy structure where we start with a primary and land on its shadow, or the other way around. And you have just a bunch, you add just with a bunch of derivatives. And so while the wave function that's associated to this sub-leading soft graviton doesn't have an asymptotic symmetry interpretation, it's not pure gauge, via this conformal multiplet structure, we can discuss it in the same kind of language. So you don't have to have pure gauge to discuss all the soft symmetries. Okay, so let's see. I wanted to say a little bit more about the infinity of soft symmetries that arises which do not have any sort of known asymptotic symmetry interpretation. But maybe I'll just sketch this because Yeah, so I was just gonna say this and then we break. That's why I said I'll make it short. Yeah, so let me just sketch it. The details are then in the notes or can be looked up in the papers. So if we look at operators which have, so if we look at wave functions with increasingly negative dimension, we will find a tower of soft states for certain values of this delta. And let me just write this maybe. So if I take the limit of delta goes to minus n, delta plus n of an operator O delta, then these define an infinity of soft operators. I think for gravity would start with -2, -1, 0, 1, and so on. And they pick out the omega to the n term in the momentum basis of an operator O omega WW bar, so they pick out a certain mode in the expansion. So they pick out this mode as omega goes to 0. So there's this infinity of modes that one can group together, and it has been found that they actually satisfy a very nice algebra. So I can define now, let me define a discrete family of positive Felicity gravitons. Let me label them, so K will play the role of the dimension. So here this operator has dimension K plus epsilon, and it has a positive spin. And we take this K to be 2, 1, 0, -1, and so on. And this operator has dimension H and H bar is K plus 2 over 2, K minus 2 over 2. So this is just, if you want to read off what delta and J means here in this weights, let me. Okay. Now I can look at the mode expansions of these HKs. Okay, let me just do this. HK of WW bar expanded in a certain range, so that will give me this mode HNK which is a function of W, and I expand this into C bars. And the range here is from K minus 2 over 2 to K plus 2 over 2. And then it turns out that these modes, if I regroup them, so I introduce new modes. Okay, now I have a problem with letters. Let me call that Z. That's Z bar. So let me call these new modes. These new modes are related. Okay, this is not important for illustrational purposes, but there's the Newton's constant. And then I will redefine the modes with these bunch of factorials and introduce these numbers P and Q. And these numbers P and Q, because K, so n ran from, was in a certain range between K minus 2 over 2 and K plus 2 over 2. Also the P's and the Q's will be in a certain range. So Q and P will be 1, 3/2, 2, etc. And once you have done this, what you will find is that these modes satisfy a nice algebra that has a name. So let me write down the algebra, and that will be the last thing that I write before the break. So this is given by following expression. P plus Q minus 2, M plus N. And this is known as the wedge algebra of W1 plus infinity. And that's an algebra that appears in many different places. It appears in self-total gravity, in N equals 2 string theory, in many different places. And a lot of the recent activities, so this is stuff from this year, and up to like a month or two ago, a lot of interest is in understanding what the implications of the appearance of this algebra means for celestial CFT. And maybe this would not have been, that there's this nice symmetry group, this would not have been so apparent if we worked in the momentum basis, where we just have the expansion in energy in 1 over omega. But once we go to the conformal basis and find these orders in the energetically soft expansion get spread out into certain values, discrete values in the complex delta plane, one finds that there's actually some nice structure there. And the subalgebra of this is given by the Lorentz, or the centerless Versor algebra. And yeah, a lot of discussion at the moment goes into what this means. Okay, so maybe this is a good time to break. So this is really stuff from a few months ago. Yeah, let's break, and then in the next, the remaining time, we will discuss collinear limits and OPEs, and if there's time, I will make a few comments about infrared divergences and conformal dressings. Okay. So just to point out that before the break here in this diagram, I made a typo. I wrote essentially the same values of J and S as in the right diagram, which we discussed in detail. For the ones that we call type 1, you actually start with a primary that has the magnitude of J being equal to S, and then it descends. So just to point out, if somebody doesn't catch this, the discussion in the break. And now, for the remaining time of this lecture, I want to discuss, so until now we discussed a lot about singularities that appear when we take amplitudes energetically soft, or the corresponding celestial amplitudes conformally soft, and we get this rich structure of conformally soft primaries that fit into these multiplets and that have this nice, that obey a nice algebra. But there's other limits that are very important for celestial CFT, in particular the collinear limit of amplitudes, which extracts the singularities in the OPE of operators in this two-dimensional celestial CFT. So collinear limits in amplitudes arise, well, we take momenta Pi and Pj of two particles I and J to be collinear. So in particular, let's say, so the Pi's are given by some energy omega I q mu, and then the Pj will be given by some omega j q mu, or I and j. And then in the collinear limit, we take these q's to be equal. And we form essentially a nearly on-shell internal particle. So there's a 3-point vertex between the I and j and this internal particle. And so we get a propagator, an internal propagator. That is proportional to 1 over Pi dot Pj. So here we're considering massless particles. And then this propagator, if I again use the parameterization in terms of the points on the sphere, in terms of, well, we discussed in terms of W and W bar, but for now let me use Z and Z bar because that's it will look more familiar. So this propagator here will diverge as 1 over Zij as we take Zi to Zj. And similarly, it will diverge as 1 over Z bar ij if we take Z bar I, Z bar j. Okay, so for the purpose of the next half hour, so we will restrict to the situation where we treat the Zs and Z bars as independent, and then we will just focus on this sort of holomorphic collinear limit. Okay? And this essentially takes us from, so we go from the celestial plane that was spanned by these Z and Z bars, and now this becomes Lorentzian. We go to 2,2 signature in treating Z and Z bar as independent. Okay, so schematically, So we have an amplitude, and we will then Vlan transform that and view this as a correlation function of operators. And when we take two of those operators of energies omega collinear, that translates to in the new conformal basis to extracting the OPE of these operators in terms of these OPE coefficients here. And these operators are then labeled by delta and j. So in this conformal basis, schematically, what we have is the situation like this. We have an operator of dimension delta I, j, I at the location zi, z bar I, and an operator with delta j, jj, at zj, z bar j. And the OPE will schematically look like this. We have this 1 over zij, singularity, and then there is some operator delta k, jk, at the locations at zj and z bar j. And then there are other terms here, which will have zij to the power 0. Oh, and I should say that what I call zij is just zi minus zj, if that was not clear. Okay, and in the following, we will now determine what the actual coefficient is that arises in this OPE. And we will do this in two ways. Maybe, well, two, and then there's a third one, which I will mention at the end, but we will do this in two ways. First, we take explicitly the collinear limit of amplitudes and Vlan transform that. And second, we will use dimensional analysis to fix what the conformal dimensions are that appear in this OPE, in this operator on the right, and then determine the coefficient just from looking at what the symmetries tell us. Okay? So first, let's do OPEs directly from collinear limits. Okay, so what we have is, we already know that the collinear limit means that zij goes to 0. So we take zij goes to 0 in the amplitude.
Sorry, Andrea, in usual CFT, there's a power on zij.
Yeah, so here this comes, so the leading OPE coefficient here will come from essentially by looking at this propagator. And from this propagator, if you write out the Q's as the one that I've given you on a previous board, you will find that this goes like 1 over zij. Now,
so the amplitude tells you, the amplitude basically tells you that the power is always 1 over z.
Yes, and then we can have powers of z bar here. And in particular, if we sum of all the descendants, there will be different powers of the z bar ij's here. In particular, in gravity, if we take these operators to be two gravitons, then the OPE will also contain here a z bar ij. Okay, so
I actually independent.
Maybe you're bothered by the fact that when we have t and t, you will get you should get a different power here, and I will come back to like the stress tensor OPE at the end.
Which is special.
Yeah, so it's special in the sense that you construct it from an operator that has dimension 0, but you also do a shadow transform.
I see.
Because the stress tensor is a dimension 2 operator, and this is obtained via shadow transform of a dimension 0 operator.
So in CFT, so the power in CFT of this zij is basically delta k minus delta I minus delta j. So does this impose a restriction on what delta k is, or?
I will write down what delta k should be, yeah.
I see. So it will be like in CFT with a particular restriction.
It will be related to delta I and delta j, and it will also be related to the dimension of the bulk vertex that this collinear limit is associated to. And I will get to that.
I see. And another question, so when you Vlan transform your amplitudes, do you get something that's holomorphically factorized or not in Z and Z bar?
Yes, so we haven't discussed explicit examples, but for example, if you take the 3-point amplitude, so you go to 2,2 signatures so that you have non-vanishing 3-point amplitudes. If you consider the scattering process, so an MHV amplitude for, let's say, 3 gravitons or 3 gluons, then you get the factorization in the Zij's and the Z bar ij's. And let's say the holomorphic one looks like a vanilla 3-point function with 1 over Zij to the powers with deltas and j and so on. And then the Z bar ij part will contain delta functions. So this will be given by delta functions Z bar ij's. And that's related to, this is one of the strange aspects of the correlators in this celestial CFT, and one may get rid of all these delta functions by doing the appropriate shadow or light transforms on some of the legs in this amplitude. So that one gets just a like factorized product of 2 3-point functions in the Z ij's and Z bar ij's.
I see. That's for, does the story maybe simplify if you're scattering massless scalars? Like, are those more generic?
So I think if you scatter 1 massless and 2 massive or the other way around, then what you land on is a nice looking 3-point function.
Holomorphic of
Nicer than the ones that I just said, also holomorphic. But I don't remember now the exact expression, but this has been computed. And various other examples have been computed. But there's not like a full, here are all the possible amplitudes and what they look like in CFT yet. It's often a case-by-case study, because if you go to higher and higher points, the integrals become more and more complicated. In particular, beyond 5 points, you have no more delta functions from energy momentum conservation that you can use, so it's more complicated. But in many cases, it has been done. For example, for gluons, it has been done up to n points in generality, and you get like Gelfand hypergeometric functions appearing and stuff like that. But so high points are difficult because of the integrals. Low points are, first of all, conceptually, because you have to switch to 2,2 signature. And also because of these delta functions, it's also a bit more tricky. And to turn this delta function into something that looks more like in the CFTs we're used to is also current research, like things from the last few months. So this is very new. And these delta functions certainly have led to a lot of confusion or made things more difficult in trying to understand what's going on. There's a lot of distributions that appear all over the case. Also the ones that in this conformal multiplets that I discussed, the bottom guys actually should be conservation laws for currents, which are 0, but actually they're only 0 up to contact terms. So one has to be careful about contact terms also in order to get everything right about asymptotic symmetries in the relation here. Yeah, so things are a bit subtle.
Sorry, is it disrupting too much to ask? What is this business about 2,2 signature? Having to...
This business about 2, signature is like if you have, let's say, an MHV amplitude of this type, so plus helicity and minus helicity, gravitons, gluons, or whatever. In 1,3 signature, they are 0. You go to 2,2, then you complexify, you treat the Z and Z bars as independent. So that's the business here. And what this means in celestial CFT is that you go from the celestial sphere to a celestial torus, or from 1,3 Minkowski space to what people call 2,2 Klein space. And then there, instead of talking about shadows, you talk about light transforms. Now you are in Lorentzian signature instead of Euclidean. There are things that become more clear, but also things that are more difficult. Okay.
Sorry, I have a question about follow-up of what Monica was asking. Just the OP expansion that you have written, from there can I write that delta I plus delta j is delta k minus 1? Is that equation right?
That depends on what your theory.
Because I'm just calculating, I'm doing dimensional analysis. On the left-hand side,
yes,
is delta 1 plus delta I plus delta j.
So for, okay, I'm going to actually do this, but if you want, if we're looking at, so we can do effective field theory and then look at the bulk vertices that would contribute to this collinear process. And okay, what's the formula? So if you have a vertex for, so in general, you would have like vertices with some number of space-time derivatives. And then some fields phi1, phi2, phi3. And if we have gravitons or also gluons, then the bulk dimension of these fields is 1. And then you have this number of derivatives. So you would have 3 plus this number as the dimension of the bulk vertex that contributes in this OPE. And so the conformal dimension here would be fixed by delta I plus delta J. So these deltas are related to the energies before Mellin transforming. So delta K will depend on the sum of those. Then it will depend on the number of space-time derivative, which are called this, give this symbol here. And then also this propagator will each have an inverse power of omega I and omega J. So you have to subtract -1 for each of them. So that would be a -2 here. So that's the general formula, and we can write this in terms of the dimension of this vertex, delta I plus delta J plus dV -5. And then in Einstein gravity, dV would be 5. So 3 plus 2, because we have something like DHH. And then this would just be delta I plus delta J. But then if you consider different, for example, you could consider different processes. You could consider that these are, one is a gluon, one is a graviton. You get a different vertex. You get a different dV here.
So the first term on the right-hand side, this 1 over Zij. So so there is a dimensionful quantity missing over there, right? Else, I mean.
Yeah. So there's also a Z bar Ij. Is that what you referred to? So I didn't write this.
Yeah. Right. That's what I was.
This is a proportional. Okay. This is not like the twiddle will be like the leading OPE coefficient, which contains everything.
I see.
And this is just proportional. Yeah.
So there is some Z bar term missing that will add up the dimension. That will make the okay. Fine. Yeah.
Great. Okay. So, but let me continue with doing this brute force from the collinear limit of the amplitude. So this will contain some n particles with helicity L1 to Ln and momenta P1 to Pn. And this can be shown to be expressible in terms of a sum over the helicities plus or minus 2. So here, since for all of the lecture I've considered gravitons always, I will here also consider the OP of two gravitons. You can do this for other spins too, but I'll focus on gravity here. So you can show that you can write this endpoint amplitude in the collinear limit in terms of a function, which is called linear split function, which depends on the spins Si and Sj of the particles that are taken collinear and their momenta. And then the remaining amplitude, L1 to Ln without those guys. Or rather, the Pi and the Pj's sum into P, capital P. And then there's also plus order, the plus dot dot dot. Let me just not be precise here. And then this P here, P mu, is given by Pi mu plus Pj mu, which I have written there. And we can express this in terms of an energy omega p, Qp, where Qp is the same as Qi, is the same as Qj, and omega p is the sum of the energies. And for the case of gravity, where I consider both these operators here, we can consider the case where both are positive helicity or negative helicity or a mixed version. Now I will focus when both have helicity +2. So Si and Sj are both +2. And then this function is given by, there's a Newton's constant. Then there is Z bar ij over Zij, omega p square, omega 1, omega I, omega j. Okay? Then what we want to do is we want to take this object, plug this function in, and then Mellin transform in omega I and omega j in order to extract the OP of these operators with definite conformal weights. To do so, we'll change variables, where omega I is t times omega p, and omega j is 1 minus t times omega p. And then this integral, this Mellin integral, the omega I over omega I to the delta, and the omega j times omega j to the delta, so this is delta I, this is delta j, contains this integrand, which is the split function, times the rest of the amplitude. But the rest of the amplitude turns out to be independent of this t. So when we change variables, so there's the rest of the amplitude, but then when we change variables to t and omega p, which now ranges not, where the range of t goes now from 0 to 1, then we have t to the delta I minus 2, 1 minus t to the delta j minus 2, and then a remaining integral in the omega p. And this is the rest of the amplitude, and here I forgot to write the important piece, which is the Zij bar over Zij. Okay, and now, since the remaining amplitude doesn't depend on t, I can perform this integral. And what this integral gives us, if you, well, you may recognize this. This is just the Euler beta function. So this is Euler beta function b of x and y, where this is gamma of x, gamma of y divided by gamma of x plus y, and x and y I call the exponent here x minus 1, and the exponent here y minus 1. Okay, so what we see here already is that in the collinear limit of amplitudes, the OPE will contain this ratio of gamma function, this Euler beta function. And now if I compute the full Mellin amplitude in this limit, Zij to 0, and I denote the full Mellin amplitude, so the Mellin amplitude of this expression by curly m, which now I think I omitted here that there is also like the helicity of the, I guess I can write S since I am looking at positive helicity. So this full Mellin amplitude, which depends now on delta I, Zi, well, it depends also on delta 1, Z1, Z bar 1, the delta I, Z bar I, the delta J, Zj, Z bar J, and delta n, Zn, Z bar n. In the collinear limit, what this amounts to is, by plugging in what we just found from this Mellin integral, minus kappa over 2, Z bar ij, Zij, then we have this Euler beta function, and we read off that this is given in terms of the delta i's and delta j's. So this is delta I minus 1, delta j minus 1, and then we have the remaining amplitude, remaining Mellin amplitude. Now in terms of the 2D spins, so the 2D helicity, the 4D helicities from before become the 2D spins. And what we have then here in the remaining amplitude is everything from before, except that now delta I and delta j. So you can read off that in the collinear limit, the dimension that appears here is delta I plus delta j, and Zj, Z bar j, and then delta n, Zn, Z bar n. And then this here, the plus, would correspond to terms that have Zij to the power 0. And then, okay, you can read then off from this expression what the OPE is when you interpret this Mellin amplitude as a correlation function of operators. So what we have written before, the O delta I, and I'm writing this now for positive helicity gravitons. So the OPE of these two operators with dimension delta I and delta j, and helicity plus 2 or spin plus 2, is then given by minus kappa over 2, so bar ij over Zij, Euler beta function of delta I minus 1, delta j minus 1, O delta I plus delta j, and spin plus 2. And if you remember back a while ago, we were looking at the Ward identity for the supertranslation current, which arose from a derivative of an operator whose dimension was taken to 1. So this is just an aside. But if I have an operator of this form, O delta plus 2, and I take one of these operators to be this conformally soft operator where the dimension goes to 1, and I have this z bar derivative, what then this amounts to is something that looks like just 1 over zij with the kappa here, and then an operator whose dimension, let me take the ith one to be this object, zij, where now the dimension of the jth operator, so this guy, is shifted by 1. So this was delta j we take to 1, sorry, delta I we take to 1, and then in the OPE of this conformally solved operator, so I plug this in here, with an operator of dimension delta j, we get an OPE that's of the form 1 over zij, and the dimension of the jth operator is shifted by 1, and this 1 is the delta I. And this was, so this is the effect that super translations have in the OPE with an operator. We wrote this down before, but just to go back and remind you, if one of the operators is conformally soft and it has this extra derivative in z bar, here in z bar I, then the OPE with an operator of dimension delta j will give an operator of dimension delta j shifted by 1, and we have just 1 over zij here in the OPE. So this was just an aside. Okay, and similarly, you can look at the OPE of opposite helicity gravitons. So let's now take, let's say this guy has -2 helicity. Then we get a different split function, and the OPE will look a little different. Essentially, the delta j -1 will become a delta j plus 3. And then here we also have an operator with negative helicity. Okay, so now this was the discussion of how to extract the OPE of gravitons by directly computing the Mellin transform of the collinear limit of amplitudes. And what I'm going to do in the remaining time is show how this arises from the action of symmetries. Maybe we can get rid of that. Okay, so we already discussed what kind of conformal dimensions have to appear in the OPE. So I can already write the schematic structure of what the OPE looks like. So we wrote that delta k has to be delta I plus delta j plus the dimension of the vertex -5, and we restrict again to Einstein gravity so that we just get delta I plus delta j. So the general form, let me just write it down again, and now it will be useful to just fix I and j to be 1 and 2, because there will be other i's and j's and so on running around here, just to not get confused. And I'm starting again with positive helicity graviton OPEs. So we already know now from dimensional analysis what kind of object should appear here. In particular, depending, okay, I'm fixing plus helicity, so this function, this OPE coefficient here, I denote by C+. If I use opposite helicity gravitons, there will be a minus here. They depend on delta 1 and delta 2. And then the operator that appears here has delta 1 plus delta 2 as their conformal dimension. And spin plus 2. Okay, so and now we have to determine what this coefficient is, which in this analysis arose just from the integral, the Mellin integrals that we do on the split function and gave us the Euler beta function. Now we don't want to do this, we want to use symmetries to determine what C is. Okay, the first thing that I want to remind everyone again, which we wrote down many times already, is that we will use soft symmetries in order to constrain this. And this is what I have written down a few moments ago. I'm going to writing it down again, because what we're now going to use, in addition to the leading and subleading soft graviton, is the subleading soft graviton, which we haven't really paid much attention to so far. And then there's further omega to the higher power terms. Okay, we talked about this term and this term quite a bit. What we will be using here is in particular the leading soft graviton theorem, which I remind you is given by this expression for this conformal factor. So eta is again plus minus depending on whether we have insert an outgoing or an ingoing soft graviton. Pj is the moment of the hard particle. Epsilon is the polarization vector, or the square of it is the polarization tensor for the graviton, and q is this null vector. And this one we had two, but we will not. This will not give us a constraint here, but this one will. So the subsubleading soft factor will give us a constraint. Let me just write down what it is. Now instead of the momenta dotted into epsilon, we have the angular momentum dotted into both epsilon and q, the whole thing squared over pj dot q. From this, you can see that if this q was the k, you have k square up here, omega square up here, omega down here. So this is really this term is really of order omega. Okay, and now we use again the parameterization where the p's, the pj's, and the q's are given in terms of. So this is given in terms of the energy, and then some function of zz bar or zj z bar j, and similarly the q is this null vector that depends on z and z bar. And in this parameterization, these expressions take a very nice form. So the z's come from the q, and the zj's come from the pj's. There's a factor of omega j, which comes from this pj square over p over pj. And this guy also takes a nice form. Yeah, okay, let me write it. Just so we can follow through with a few steps. So there's also z bar minus z bar j divided by z minus zj factor out front. And then the rest, once we go to the conformal basis, so there will be omega the omegas here, which in the conformal basis we can replace by the h's, the weights. So yeah, this looks a bit technical, but this is just so you have an idea of what these objects look like. In particular, this guy here is a bit special in the sense that there is a 1 over omega j that arises here, and this will essentially, in the conformal basis, become an operator. So remember, we defined this operator omega hat, which shifts the conformal dimension of an operator by +1. Now this 1 over omega j will become an operator, essentially an inverse energy operator, which shifts the dimension down by 1. Okay, so this is just to give some details here. And now what we will do is we will use the leading and the sub-subleading soft graviton theorem to constrain this C. And we will also use translation symmetry. And then we can fully fix what this C is. So the first thing is that we use the leading soft theorem to fix the normalization. So if we take delta 1 to 1 of O plus, not O plus, of O delta 1 plus 2, Z1, Z bar 1, and this remains general. we find that this should behave as follows: minus kappa over 2 divided by delta 1 minus 1, z bar 1, 2 over z 1, 2, O delta 1 plus delta 2, z2, z bar 2. And there's this pole here, and remember when I wrote down before the OPE where we used the super translation operator, I had this factor of delta 1 minus 1 on the other side. So here, if I don't multiply here by delta 1 minus 1, I get this pole. And this implies on C the following constraint, that if I take the limit of, so this means that the OPE coefficient will have a pole at delta 1 is 1. So that means that the residue, so multiplying C by delta 1 minus 1, and then taking the limit, means that this has to be 1, or rather it has to be this factor minus kappa over 2. So the leading soft graviton theorem fixes the normalization of this OPE coefficient. So that's the first thing. The next thing is we're going to use translation symmetry to constrain, to get a recursion relation for this C. So remember that this operator P minus a half, which was just plus minus, so that's eta, it's plus minus depending on whether it acts on a in or out states. And then this energy operator omega hat, which shifts the conformal dimension by plus 1. So that means that if I act on an operator delta J with this, let me call it, let me denote it by 0 because this is the global part of the leading soft graviton theorem. So this means that this operator gets shifted conformal dimension. And if I now act with this on both sides of the OPE, so for delta 1, delta 2, and then this will give me a constraint or recursion relation for C. What this will tell us is that C delta 1, delta 2 is to be equal to C delta 1 plus 1, delta 2, plus C delta 1, delta 2 plus 1. Okay? So this comes from acting on the first and the second operator, and we arrive at this recursion relation. This doesn't fix us the OPE yet. So we can look at more symmetries, how they constrain the OPE. It turns out that by looking at this leading OPE coefficient, we don't get more constraints from the subleadings of graviton theorem, but we do get one from the sub-subleading one. So this soft factor, written in the conformal basis, we can look at what the action of this is on an operator of dimension delta, and this will give us an extra recursion relation. So I think we are sort of running short on time, so maybe I'll skip the details here, just to say that, so this was translation symmetry, so the global part of the leading soft graviton theorem, and then we have the subleading soft graviton theorem, which arises from this guy, and this guy will give us an action, let me call it, denoted with a 2, on some operator delta plus 2, which is some expression that contains the delta 1s and delta 2s. And this will give rise to a recursion relation similar to this one, but more complicated. I don't know. Do people want to see more details, or should I just jump to the conclusion? This doesn't look so bad if I look at the action of when we set to 0 z bar 2, then this action, and okay, to be consistent with the lecture notes, let me put the bar here. This is just given by minus kappa over 4 delta. Let me put delta 1 here. Delta 1 minus 2. Delta 1 minus 3. O delta 1 minus 1 is 2. So I get recursion relations like that from the action of this sub-leading symmetry. And then at the end of the day, so this is the action, and then I get a recursion relation that's more complicated than that. And then at the end of the day, you can try to solve this recursion relation. You already know the normalization, and you have two recursion relations. And so this gives you, at the end of the day, that C plus, well, unsurprisingly, has to be given in terms of this Euler beta function. And in order to get here, you use these recursion relations, and you also use what's known as Vlan's theorem, where if you have a function x, f of x, so you have an equation like that, this equation is solved. There's a unique solution which is given by the gamma function. And so from these kind of recursion relations, this one of the more complicated ones, you see that you get a structure like this, and that's how this ratio of gamma function appears in the solution to these recursion relations. Okay, so, and a similar story can be done for the opposite, when we have opposite helicity gravitons in the OPE, and unsurprisingly, we will find that we get the same result as from this collinear analysis. Okay, so now we computed from the collinear limit and from the consideration of dimensional analysis and symmetries alone, the OPE coefficient between two gravitons of arbitrary conformal dimension deltas, delta 1 and delta 2. Of special interest is, for example, the OPE of the stress tensor, which we can obtain, for example, by doing this Mellin transform of the collinear limit, and by taking into account that in this amplitude, we should also have the 2D shadow transform appearing, because the stress tensor is a shadow transform of a dimension 0 operator. And if you do that, so the stress tensor looks something like this. It's the limit of delta goes to 0 of an operator with dimension, well, operator of dimension 0, but shadow transformed. And this is given by, okay, maybe I don't get the factors here, it's not important, but this is essentially a 2D integral, so in the 2D coordinate of, so yeah, let me write this first, of an operator whose dimension is taken to 0. And because the shadow transform flips the spin, if I want to end up with, I guess there's a minus here, if I want to end up with the stress tensor with h and h bar being 2, 0, instead of 0, 2, I start with an operator that has negative spin here. Okay. Yeah, good. So here we would have, what do we have? So this is, we have 0, so minus 0 plus, yeah, minus 1 plus 1, right? And then this comes from z minus w to the 2, 1 minus h, where h is now minus 1, so this becomes 4, and there's also a factor z bar minus w bar to the 2, 1 minus h bar, and since h bar is plus 1, this is 0, and that's how this 1 over z minus w to the 4 arises. So that's the stress tensor in this 2D CFT, and now I can write down what is the OPE. Well, first let me write down the OPE with an operator, general operator of dimension delta and spin j. That is given by the weight of this operator, z minus w square delta j, plus 1 over z minus w dw O delta j. So this is a primary operator, as you can verify from this OPE. And then if I take two stress tensors, then the OPE is given as follows. And here you notice that we don't have a central extension here, which from this analysis of taking collinear limits and Mellin transforming, we cannot get. Okay, so this is all very much consistent with what we know from CFT, and it better had to be, because we are just making a mathematical statement of writing of the isomorphism between Lorentz transformations and SL2Z global conformal symmetry, and the extension of global conformal symmetry to local conformal symmetry, and so this is what we expect, and indeed this is what we get. Okay, so I think I have run out of time, so maybe I'll just make some concluding remarks of other topics that we haven't covered so much, but maybe first let me ask if there are questions. While I start erasing.
So in these OP coefficients that you have derived, you basically have an explicit form for the OP coefficients between two gravitons, and those you have derived only using the symmetries and IR properties of these gravitons.
Yeah.
Like amplitudes in collinear limit and so on.
Yeah.
So, but my question is, how are we saying that basically also like the UV properties of the interaction between these gravitons are determined by this IR information? Because I mean, if these OP coefficients are valid in general for these two gravitons, you're saying that we were determining like with these OP coefficients, then using the fact that the scattering amplitude is a correlation function in the celestial CFT, you're basically determining all of the scattering amplitudes. Is there some like cutoff in the UV, or are we really like determining UV interactions and data from IR?
So, okay, maybe the first comment here is that since we're integrating from 0 to infinity over all the energies, UV and RR are not clearly separable. We saw that when we look at the low energy sector and we Mellin transform, that we get that the low energy expansion, the 1 over omega expansion, translates into spreads out into these poles in the delta plane. So that was fine. But in general, even writing down amplitudes, Mellin amplitudes, so celestial amplitudes that are well defined, is not generically you don't get that if you look just at classical scattering, say. So for example, the 4 graviton amplitude, or even the 3 graviton amplitude, if we go to 2,2 signature, contains a remaining integral that blows up. And so in order to really talk about well-defined celestial amplitudes, you really also need to talk about the UV. So there, okay, what I didn't talk about is some constraints that you get on the UV, or that the UV, that you use, if you have constraints from the UV, say you go to string amplitudes, so you compute the Mellin trans celestial string amplitudes, you will find that divergences that you had, if you didn't include the softness of string amplitudes, so these divergences will go away. So you can make celestial amplitudes well defined by going from the low energy amplitudes to string amplitudes. Also, when you do a low energy sort of effective expansion and write down amplitudes, and then you have some behavior of the amplitude in terms of the energy, because you're integrating over the energy, that will translate for you to certain poles in the delta plane. And if you go to a well-defined soft UV for these amplitudes, some of these poles will disappear. So this is about analytic structure, that where the UV, so in the celestial amplitude somehow it's built in that you have to either use some UV information, or UV physics will be constrained by the well-definedness of these amplitudes. So, and this is also very much a sort of work in progress, like from the last year essentially. And we don't really know a lot about this yet. But for example, string amplitudes have been written down, and they are very nice. and they cure some divergences that come from some remaining energy integrals that blow up because of the powers of energy. So for example, the 4-gluon amplitude is just marginally convergent because there's a remaining integral in the energy which can be interpreted as a delta function, which gives a constraint on the conformal dimensions. But then for gravity, the amplitude has an extra power of the energy, and so this can no longer then be written as this marginally convergent delta function, but it blows up. And so classically then these amplitudes are not really well defined, but you still can look at, for example, properties of factorization without worrying about this extra divergence. You just keep this integral along for the ride, and you can relate low and high point amplitudes in this conformally solved factorization, for example. Yeah, but there are many things that are not well understood yet, and the UV behavior is a very important one, and so there is interesting room for string theory or for general constraints from quantum gravity that will be very important to understand here.
Okay, good. Thank you.
Sorry, was there another question? Okay, so UV will be important. Other things that we haven't that I haven't discussed, but so one can look, for example, if these amplitudes satisfy crossing. One other interesting thing is how unitarity manifests itself, or causality or bulk locality. There have been some interesting recent papers discussing these issues. Then, since we talked about the UV, we can also think about the IR, where we have divergences that come from loops, which I did not get to talk about. So essentially, we have infrared divergences, and in order to have a well-defined S-matrix, what do? Traditionally, we look at inclusive cross-sections that can be compared to experiment, but we would also like to have a well-defined S-matrix that is finite, infrared finite. To do that, we should replace, so it was proposed many decades ago, that we should replace the Fock states by asymptotic states that sort of take into account that we have soft radiation, and these asymptotic states have been called, well, Bardiev and Kulish. Bardiev and Kulish studied these. So these asymptotic states can be interpreted as Fock states with an infinite number of soft bosons. So we see that soft radiation is very important for canceling infrared divergences. And recently that has been reinterpreted as saying that, well, so the infrared divergences exponentiate. And then if they exponentiate, well, the amplitude is 0. But then if you use these Bardiev-Kulish states, you can make them infrared finite. And this has been recently interpreted as due to, well, it has been connected to asymptotic symmetries. So the amplitudes that vanish because you don't conserve the charges associated to these asymptotic symmetries. So for example, BMS charge conservation, if the amplitude satisfies it, it should become an infrared safe quantity. And this is mathematically not a new statement. It just says that Bardiev-Kulish knows about asymptotic symmetries in a sense. Okay, so there will be a section on this in the lecture notes, and you can go also to some recent papers which will be referenced in there, including by Sang-Min. So if you have questions on dressing, you should go and ask him. And these so Bardiev-Kulish dressings, they don't span the full space, and also they're over-complete within the range that they span. So there's various questions about those states. But it turns out that in the discussion of celestial CFT, there's one particular dressing that gets singled out. Let's call this conformal dressing. So, okay, so what I mean by this is that now you dress the states, you dress the states in a certain way, and that makes the amplitudes infrared finite. And there exists a particular choice of dressing, which we call conformal dressing. And that dressing has the fact that, okay, let me write down just two more equations. So one can show that amplitudes factorize into a part that contains the infrared divergences, and then a hard part which does not contain any UV or IR cutoff information. And then one can show that this soft part here, if you Mellin transform this whole expression, this soft part can actually be written as a correlation function of, so an exponential of operators. Let me just be schematic, where we have this energy operator, remember this from translation symmetry, and then some function of z and z bar. So this should be inside. And this function here is nothing but the Goldstone boson, which we have encountered earlier in the lectures. So it's the Goldstone boson of spontaneously broken asymptotic super translation symmetry. So if you remember, if we take dz squared, so zzz at the boundary, square plus minus, can be written as dz squared of some function c, and this is this function c, the Goldstone boson of spontaneously broken super translation symmetry. And moreover, this Goldstone boson, to connect this to this conformal multiplet structure, this can actually be, so every conformal multiplet that contains asymptotic symmetry generators that I've drawn has a canonically paired multiplet. And in particular, for the one that contains the super translation charge, there's another conformal multiplet that I can draw, where this Goldstone boson sits inside this, celestial diamond. So I got a question, I think in the last lecture, whether we also consider operators that sit at the bottom of such a structure. And remember, we just discussed this diamond where at the bottom we had this soft operator for super translations. So this diamond that contains the information about soft charges is canonically paired with this diamond that contains the Goldstone mode for this symmetry. And I'm out of time now, so I will just say that this is a very interesting structure, that this factorization into this correlation function that involves these Goldstone bosons. And moreover, if we now use this Faddeev-Coolidge state, so we dress every hard operator in this hard amplitude by a certain dressing that will also involve this C, then this dressing will appear with the opposite sign here. And so we will find that this soft factor, which contains this correlate of these Goldstone bosons, and the dressed, the amplitude for the dressed hard states, so these factors cancel. And at the end of the day, we will just end up with a dressed amplitude, which is given by the hard amplitude. Okay, so I did not have time to go into details here, but there's some interesting story for how this conformal basis, in particular the modes that appear here, make certain structures that we have known for some time, express them in a very nice way. And in particular, these operators here, so the fact that this soft sector or conformally soft sector sort of factorizes out means that we should be able to find an intrinsic 2D description just of the conformally soft sector. And there have been recent works that discuss these modes, so these top of the diamond modes, and what their physics is, and finding actions for these modes, so that we can describe the conformally soft sector of celestial CFT intrinsically in 2D language. Yeah, so that's some of the main things that have been going on in this celestial holography program over the last few years. And this is a work in progress, so there's many new directions that emerge every other time. And yeah, I think I'm going to stop here.
Thank you, Andrea, for the very nice lecture. Any questions for the lecture or for the course? I'm very bad.
So the celestial CFT is most naturally defined on the sphere in this construction, right?
Yeah.
That's what pops out from the 4D asymptotics, I mean.
Yeah, you could also do the celestial torus if you want to go to 2,2 signature.
I see. You're saying that that's what you get at infinity if you are willing to do these rotations.
If you, what I mean is that if you change from 1,3 to 2,2, then the natural discussion is in terms of a celestial torus, and there has been some work on that in the last year, like this year. So
I see.
it hasn't been really fully exploited yet. It has been discussed for, I think, scalars.
I'm trying to get at that, because often when we talk about 2D CFTs and their consistency and their properties and their spectrum, we put them on a torus. And for example, we want to make sure that their spectrum is modular invariant. So at the level of what we talked about in this course, that's all totally invisible. But has there been any understanding of whether the celestial CFT could satisfy that property, or what that implies about the bulk theory in reverse?
Yeah, that's a very interesting question, and it's one that hasn't been, I think, possible to ask before 2021. So yeah, it's one question that certainly will be looked into, but I don't think there is a statement at this point. Maybe some bits of information, but there haven't been many papers on this. Yeah, so we really went up to 2021, including results from the last few months. So there's many open questions.
So is it a general statement that if I want to put the CFT on a homogeneous surface, that I mean, you mentioned this connection to changing the signature in the bulk. What do I imagine doing if I'm trying to put the CFT on a genus 2 surface, say? Which I'm free
for
to do
example, if you allow
conformal.
for these singular superrotations, you would pierce the celestial sphere at certain points, right? So maybe that is related to this question. But in general, okay, the general answer is I don't know. Yeah, there certainly has to be some bulk interpretation of this statement, but I don't know it. Yeah, if you just consider perturbative scattering in asymptotic flat space, and you restrict yourself to Lorentzian signature, then the sphere is what you get. And you can pierce it by cosmic strings. Yeah.
Yeah, it seems, I mean, there's an opportunity to use it in reverse, in the sense that, well,
if
if you believe in this celestial CFT, then you try to use that to constrain what the 4D theory is allowed to look like under the condition, the constraint that you have to be able to put it consistently on the torus. So what does that tell you about what is scattering in 4D?
So definitely you can go to your favorite CFT book and then see what's in there, and then ask, okay, what does it mean in the bulk? And up until recently, I would say, we haven't even fully understood what the operators are, or their dimension, and how, we then understood that, okay, so the complete basis you can get on the principal series, but then we knew from examples that there are integer dimensions which do not fit into this, which we know are physical, and then we found more and more such examples, and now we have this whole tower of integer, half-integer deltas, which seems to have some meaning. There's this symmetry, but we don't know what it means from the bulk point of view. So up until recently, there were many sort of very basic things that we didn't understand, or wasn't worked out yet, because this field is very new. So now you can go to ADS-CFT and 20 years worth of, or 25 years worth of results, and ask, okay, which one applies here too? Or you go to a CFT book and you go through and say, okay, if we have this in the CFT, like let's assume we have this, then what does it mean in the bulk? Or can we not have it because we don't have this bulk theory? Or for which bulk theory do we have what kind of CFT? We don't even really have an example, an intrinsic CFT, 2D CFT example. If we had that, that would be very nice. Also, the embedding into string theory. It's not clear. We have these string amplitudes, which also satisfy these properties that we see for, like, let's say, Einstein gravity, but nicer because of this softness. But then embedding this in string theory, also in higher dimensions, that's also not clear, because we know we have soft theorems, but what are the asymptotic symmetries? And there's many questions that hopefully we'll find answers to in the next few years, including very, very basic ones. Yeah. And that includes also this question about the norm and emission conjugation, which is quite a confusing one. Do we have to reorganize our how we think about 4D scattering in order to get something, the CFT, that we are sort of more happy with? And yeah. And there's a lot of it is in the details. There's a lot of like subtleties, contact terms, and well, you have to be very careful. So this has maybe hindered faster progress, but I think there's already like a lot of exciting things, including that the power of symmetries, which are sort of front and center in this whole program, the asymptotic symmetries, and then symmetries that don't have a clear asymptotic symmetry interpretation, but we see give something interesting from the celestial amplitudes point of view. So, yeah.
Yeah, so it's maybe more of a philosophical one. So if I start doing this holographic, this flat space holography from the string theory point of view, taking some decoupling limit of d-branes, we usually, I mean, at least it seems that we will get some codimension 1 holography. Do you have any way of saying, like, you take the full D3 brane geometry, for example, and still getting a codimension 2 holography? I mean,
I don't know this answer. Would love to know it. Yeah.
Okay.
It would be very nice to, even without going to full string theory, but just from ADS-CFT and take a limit and go to this flat holography and see what happens to this extra dimension that we seem to sort of lose. Yeah.
More wild or less wild questions?
Hi. So I think in one of your first lectures you said that this formalism is not yet developed for asymptotically flat black holes, or something.
Oh, so
of the sort.
you can no. So okay, what part? So the part about BMS symmetry, you can super translate the black hole, and that's fine.
Yeah.
And that one falls into the metric that we wrote, and you can super rotate it. Then you get those cosmic strings. You have to relax your boundary conditions. What I mean here is that here we're dealing so far have been mostly constructing bottom up, starting from some perturbative scattering in the bulk. We don't know what, and even there it's many things are not clear in what we don't even know what the CFT is without having black holes in the bulk. So that will add some other complication.
Yeah, you will have to do like scattering in black hole background to derive. Okay, I see. No, because I was asking this because maybe in this program there was also a sort of resolution to the information paradox, like in ADS-CFT, where since we know the CFT is unitary, then ADS should also be, like black hole evaporation in ADS should also be unitary. But I guess there's not yet the machinery to answer this question here.
No.
Yeah.
No.
Thank you.
But that's certainly one of the, for some of us, one of the big goals, because in ADS-CFT we can discuss special kind of black holes, the highly rotating or highly charged black holes, or black holes in ADS. But on the sky, many black holes, or most black holes, are not highly rotating, so they are described by asymptotically flat space. Well, at the end of the day, everything will be in some sort of cosmology, but let's say to first approximation. And if you want to know the microstates of a Schwarzschild black hole, what do we do? And if we get this thing to work, and the celestial holography program really to tell us something new about the bulk from the CFT, once we know what it is, or what kind of theory it is, then hopefully we can say something about black holes too. But along the way, there's many other interesting things that's just about QFT and the UV completion of without even black holes in the game.
More questions? I just have a short question related to Gabriele's. So can you enhance your celestial CFT to have a time and unitary evolution and so on?
So we discussed in the first lecture that the boundary is degenerate, right? And so the metric, the induced metric, is 0 the U square plus the sphere. So I mean, I think people have, so there are works that try to give sort of a modified Mellin transform that also includes U. I don't know too much about that other than you get consistent results and you get dependence on U as well. Yeah.
in the sense, I mean, you introduced this delta, which was the Mellin transform of omega, which is the Fourier transform of u.
Yeah.
So it sounds that somehow you've hidden u in your equation. Is this a, should I think of this theory as some sort of deconstructed time direction times 2D CFT?
What is a deconstructed
like when you take a direction and you, for example, do KK reduction on it, and you work with the infinite tower of KK fields instead of working with the direction.
Yeah. So I mean, we go from as you said, from u to omega via Fourier, and then from omega via another Fourier, which is a Mellin, to delta. So, yeah. But I don't know how to. I don't even understand what this 2D theory is. What actually an example of this theory. I know there have been some works, but it's also not very, at least to my knowledge, not very developed. Surely there's probably some interesting things to understand in this direction too, but also, many other directions. There's so much to do.
Okay, so now we're done. So let's all thank Andrea for a very beautiful talk.